Okay, so welcome to the last meeting. We'll talk in this lecture about the ultimate application of a lot of the methods we've done. It won't be the model that you will end the course with, because the leading model, as you know, is the new Keynesian model, which involves a certain amount of price stickiness originating in the behavior of firms and or agents that are setting wages and in terms of the monetary unit. And that leads to very interesting complications of the model I'm about to present to you. But think of this as the baseline model that Ed Prescott and to some extent also Robert Lucas and Nancy Stokey propagated as some benchmark. And I'll try to give you some intellectual history on why that's a benchmark. Because it's a model where you're asking this almost heretical question: what would happen if we had a world where prices were perfectly flexible in terms of the monetary unit? And how would that economy behave? Could you even generate business cycles under those conditions? Okay, so that's often called the real business cycle paradigm. Kind of not necessarily littering the wayside, but it's no longer the leading way of tackling problems, but it is very useful to organize our thoughts. And Prescott, who just died recently, is a leading contributor, was a leading contributor to this idea, and got a Nobel Prize for it because the methods that he proposed are sort of an implementation of what we've done already, and are used even in new Keynesian analyses. Okay, so that's the overview of the overview. So today we're going to review briefly. I'll talk about the so-called representative agent model, Robinson Crusoe. We'll talk about it as a proposed as a proposal, and we'll solve it using the tools we've learned. We'll talk about ways of approximating the behavior of this beast, because even in its most simple form, it's actually difficult to get an exact solution, and we can't get analytic solutions except in very special cases. So we end up doing in your real world later will be to take an approximation, either a first order log linear approximation, and look at that approximated economy and look how that behaves. And maybe if you're really adventurous, you'll go to a second order or higher order approximation. And there's also ways of doing even more complex solutions to these models. And if you had come to the Schumpeter seminar, you would have seen Alexander Mayagoda, who's one of our ex-postdocs, who actually has done some interesting work in refining these methods and looking at the accuracy of these approximated models. Because a lot of times what you're interested in is maybe the behavior of economies to risk or higher moments of the distribution, and it's not possible to do that really with a log linear model. Okay, I'm going to talk about modifications of the model already possible that you can do to make this model look more and more like the real world, because really what we're ultimately interested in making the model behave like the data in ways that I've already told you about: the time domain and the frequency domain. And the frequency domain is not so, we're not so good at it. So we're generating cycles like Slutsky would suggest, but they're not really so close to what we think the business cycle is. I think it's a problem, and I think a lot of people who do time series analysis understand that. So other people may not be so convinced, but if you really want the medium-term dynamics of a response to a shock, you might want to think about this aspect. And some of those bells and whistles are quite interesting and almost standard now. I haven't taught you, but I'm sure my successor, Professor Weinke, will certainly mention habit formation, costs of adjustment, all these other tricks that you can do that make sense from the micro perspective, that give rise to dynamics that approximate the real world better. Okay, so then we'll finish up. So last week we studied this linear quadratic setup, the functional that results from it, how you can form expected discounted values, and how that can be interpreted as a value function, which I thought many of you understood and saw as an interesting insight. The idea that two ways to solve these dynamic optimization problems. One way is just the infinite period perspective. The other is to collapse it into a two-period perspective, under the assumption that my own self in the second period will behave optimally. That's all I need. I just have to be behaving the same way as I did in the first period. And then we kind of motivated the general approach. So in general, you can pretty much assume that there are two ways to solve these problems if people are behaving rationally. You can do it the standard Lagrange way, or you can do it the value function way. The value function way has the advantage of imposing the transversality condition automatically. I mean, there's, the value is optimized so it incorporates this restriction that the transversality condition would embody, and therefore you can deal with it directly. But the issue that plagues a lot of us is whether the value function exists and whether it's unique, and maybe can you take derivatives of it. But believe me, I've had lots of PhD students work on problems that involve the value function. Sometimes even looking somewhat strange, but still being able to reach a solution, a reasonable solution to a problem using this approach. And I tried to give you a little example, the value of the value function approach in a particular application, and you can use that, again, eliminating, once you've solved for the first order conditions, you can eliminate the appearance of the value function in any of those conditions and replicate, in a sense, the model's solution using Lagrange approach, the Lagrange method. Okay, so I will make this solution available probably this afternoon, and we'll discuss it anyway, so you get to see it, and we'll discuss it afterwards anyway. Okay? So I'll see you here on Friday. Okay, so think of the real business cycle paradigm, and you won't hear much about it in this macro sequence. Not because it's uniformly failed, but it was a response to a failure. It was a response to the 1970s when inflation was rising and monetary policy seemed to have very little effect on controlling the behavior of the economy. So a lot of cynics and skeptics and critics got into the action, and some of them culminated in Nobel Prizes. I don't have to tell you all this, but you know it already. Most importantly, it gave rise to this almost heretical notion of maybe we don't need this. Maybe let's go back to basics and ask whether an economy without any monetary, the limit of an economy without any money, that does it all basically by exchange with a real means of payment that has a guaranteed value. That's one way of thinking about it. So we're exchanging my labor for your food, and how would that economy behave? So again, it's a response to the critique of ignoring expectations. That's why we have rational expectations as a baseline. That was done in my generation, when I was a graduate student, and these guys made it very clear that we need expectations formation is kind of a free parameter. And you can't, if you just choose adaptive expectations, you could choose any form of adaptive expectations without any discipline. And then you can sort of design your own dynamics. And the question is that a usable model for any sort of policy? And especially Robert Lucas, but these others have said, well, if people understand the policy that's designed on people's, on a conception of people's expectations, maybe that is wrong. Maybe if you implement a policy, people will behave differently, and therefore the whole exercise was a waste of time. So that's kind of what we call the Lucas critique. So using plain econometrics based on past data, conditional on a past regime, may not tell you much about how the economy behaves when you introduce a new regime that's different. Okay, so Lucas had this brilliant paper where he actually shows that the behavior of an economy with a tax regime for investment. That was the big deal in the 1970s. One of the big deals was implementing a temporary tax incentive, and people were saying, well, if people who are putting resources in capital goods understand that this is a temporary action, will they respond very strongly? Or if they do respond strongly, maybe they'll respond just as strongly afterwards and roll back their investment. So you just have an intertemporal reallocation and not a real permanent change in response. So it's basically saying, if people are as smart as I am, Robert Lucas said, if people are as smart as I am, then they'll see through this. And I think in modesty, he was basically saying that a lot of people may even be smarter than he is, you know, and that if they're out there, then they're going to anticipate these effects. So we call this the Lucas critique. It's a general idea, and I'm sure Professor Weinke will talk about it. Okay, so this new program was basically saying, okay, well, let's start from scratch and say, what if we didn't have any money at all? What if we had a pure non-monetary economy? Could you still get business cycles? What would be the necessary conditions to do that? This was basically in 1982 and 1985. Several papers came out, well, two I'm thinking of in particular, with Edward Prescott as an author. And surprisingly, the answer is yes. Okay, so you can, and you can, we'll write down, we'll sketch the model that those guys thought about without the bells and whistles that they implemented. Okay, so they also kind of, and you have to understand, these guys were working with very primitive linear quadratic approximations to everything. And they were using, I mean, you guys are so, you know, lucky to have all the computer technology that we have today. But they were able to show quite clearly that you can get cycles and they can look pretty accurate, even though there's no inflation, there's no money, okay? And so that stimulated a huge discussion. A whole bunch of students of these guys in the 1980s are still roaming the earth today and influencing the way we think. And especially my tribute to these guys is that they basically left us with a bunch of tools that we can use even in a world where we think that prices might be sticky and that money might be relevant or that nominal interest rates could be set by the monetary authority. Okay, so it opened up vistas that we still exploit today, and the buzzword, of course, is micro-foundations. Okay, so we're talking about, again, a representative agent making plans that involve foregone consumption today for return tomorrow. So you need a production function, you need a capital to matter, you need his labor to matter, and then you have output that can be used again. So it's got this natural recursiveness built into it. It's an old idea, so it's not, Robinson Crusoe is much older, but the notion of Robinson Crusoe probably goes back to Irving Fisher in the 1920s or 30s when he was thinking about intertemporal and intratemporal choice. Okay. All right, so the idea is simply we're going to have an infinite population of representative agents that are all identical, so none of them has any influence on the market per se. They're all behaving independently. We know exactly their preferences. We know exactly the technology of producing goods and therefore moving resources from inputs into outputs and moving resources from outputs today to outputs tomorrow. So we have micro-foundations. We can really, and since we know the tastes of this representative agent, we can actually preclude the Lucas critique. Any intervention that you could imagine, you can really explicitly see how the agent would react to these interventions. So we're going to be dealing with a decentralized version ultimately of this, meaning that agents actually sell their labor and they have capital and they can rent the capital out to firms. The firms are representative agents that are maximizing profits, and the profits are remunerated to the representative agent. So it's really some people say this is nonsense, but it makes perfect sense. You can't challenge that. It's just basically a setup. Ultimately, the big progress in macro today might be made in making agents slightly different, having 2 or 3 or maybe n classes of agents that have different initial wealths, or that some actually own the firm and some don't. So we have what's called heterogeneous agent approaches. These are all variations on this idea. And of course, it gets very complicated once you do that because you have to explicitly model market clearing for goods and for factors. But we'll start somewhere. If you buy into this setup, again, this is a decentralized economy with no market power, complete information, non-increasing returns to scale. It's a really important aspect. Then we can actually apply the theorems of general equilibrium theory. There are a couple of other bells and whistles you could talk about, but generally the appeal of this approach that I'm going to show you right now is that if you solve the maximization problem for the planner, in this economy it is replicated, it can be replicated as a decentralized outcome. Okay, so that's the magic of the second welfare theorem. The first welfare theorem said is if I fulfill certain conditions, then agents trading result in a Pareto optimal outcome. The only way you can make one agent better is to make another agent worse off. And that's pretty much something you learn in micro. I'm sure you've already seen it. And there are very complicated variations of that, including all the trading at time equals 0, and trading in contingent goods, contingent contracts. So I pay €5 for a beer if the sun's shining on Tuesday, right? And then, if I take it or not, that doesn't matter, but it's going to cost something, and I get that. And if it fails, I can buy an insurance contract to compensate me if the bar goes out of business until the time I'm supposed to get my contract. So these are all incredibly theoretical ideas, but just for the sake of the argument, can we write down this optimum optimorum and then make the assertion that it could be replicated? And as soon as you deviate from those assumptions, as soon as you have firms that can set prices, for example, you've deviated from this competitive paradigm. As soon as you have increasing returns to scale, if you have externalities, if you have people with incomplete information, maybe subsets of agents with incomplete information, any sort of price setting for the final good in terms of the money unit will lead to deviations. Okay, so we're studying the best, and then we take a step down, and then we realize the rest of our lives will be dealing with the rest of the world. But you just kind of reach the lofty height, take a look from the mountain, and see what it looks like. So we talk about the central planner's optimum. The social planner, or the central planner, is not trying to optimize her own welfare, but rather the welfare of this representative agent, or this sum of identical representative agents that are all identical. And it's a stand-in. And it's often associated with Ramsey's contribution in continuous time in growth theory, or a really brilliant paper, the introduction of continuous time optimization methods. Even Keynes said that he was an impressive guy. If Keynes said that, that's saying something. Okay, so Banke will talk about the Ramsey solution to models. An optimum optimorum, possibly under constraints. You might have constraints acting as well. We always have constraints. This problem also has a constraint, the resource constraint. But you might have even more constraints. You might have a certain set of restrictions on the budget behavior of the government, or the tax rates that the government sets have to fulfill some requirements. Okay, so we're going to look at this maximand. So it's something we've already seen before. We're going to have a utility function, which is a monotone function of consumption. That's all that makes Crusoe happy. You can call it corn consumption. It's a non-durable good. It's not storable. Adding storability is fine. It just changes the nature of the problem. So we're going to talk about consumption. Crusoe is controlling his own consumption, but he's also controlling the complement of that. So given some production YT, Crusoe can plant some of that corn. Okay? And the way this model is set up in its simplicity is that there's no storability of the corn. So basically, if Crusoe wants to eat tomorrow, he better not eat today a little bit and plant it. okay? And the first derivative of the utility function is positive, second is negative, so it's a concave, very classic sort of problem. You can impose innata conditions and the rest. Well, I'll just neglect that for the time being, but in general, you would like to do that maybe to keep him from starving. So you'd really have a very, very strong incentive if C is very close to 0 to defer a little bit of consumption. Okay, so we're going to give him some planting in the ground. So he was lucky. Someone had already done some planting. There's something in the ground already. And the harvest is given by a production function that has a random component. So theta is a multiplicative shift of the production function. F is a concave production function of the capital stock, which is the deferred consumption from yesterday. Okay? So we have all these ingredients that we've seen from the past lectures. We're going to impose that this shift term has certain properties. If you take the log of it, it's going to be stationary, and it's going to be ergodic in the sense that we already understand. So it kind of visits all the states with probability 1. Okay, so now it gets really important to understand the resource constraint facing Crusoe. And again, we'll call Crusoe alternately the social planner because he's planning for himself. But in fact, he could be a stand-in for many, many consumers doing the same thing. But this is the kind of the planner problem. So capital tomorrow is equal to production today minus consumption today. And again, at this point, I've left it completely general. A linear transfer of resources is already a specialization, but I'll take this classic case, which gives us a closed form solution. So that I'll basically spend some time with Brock and Merman. These are guys that were really ahead of their time. This is in the early 1970s. And this case is still being used today because it's actually got a nice, clean solution. And we can look at it. It's got a closed form. And beyond that, we're going to have to log linearize everything. So it's my intention is just to show you that. Everyone has to see that. It was part of my graduate education in the 1980s. Okay, so if we take the log function as the consumption, the periodic utility of consumption in period t, and again, it could be much more complicated. You can have a Hara type of utility function, periodic utility function. You can have a reference. You can have habit formation. All these things are bells and whistles. But just take this at face value. Okay, so the Lagrange looks like this. The Lagrange function, we'll use the Lagrange approach to attack it. Okay, and let lambda t be the current and not the present value. So how do I know that? Well, I know that because I've got beta t on the outside and lambda t on the inside. Well, you can write this in terms of present value Lagrange multipliers. We talked about that. This is the way to do it. Okay, so now the first order conditions for the optimum are going to be sequences for the control variable, and you can call kt plus 1 a control variable from the perspective of period t. You can also call it a state variable in the narrow sense because it's predetermined. Crusoe can't change kt, but in period t he can change kt plus 1. Okay? And then you've got this Lagrange multiplier. So we'll have 3 sequences of first order conditions to characterize the optimum in this problem. 3. Okay, and they're sequences. That means for t equals 0, 1, out into infinity. That's the disadvantage of having the Lagrange approach. I mean, again, Crusoe has a discount factor, and those faraway decisions will not matter very much, but they do matter, right? So we have to keep track of them.
Sorry?
Yeah.
Just for completeness, the counterpart to the current valued Lagrange multiplier is present value?
Yeah. Present value means at t0, what's the value of a relaxation in the future, given that I'm behaving optimally? And the current value would be when I've reached t, what is the value from the perspective of t? They're identical because the discount factor is constant, is deterministic. Okay, so one can always be written in terms of the other.
And in that constraint, it would be, you said it before, that it would be outside the discounted sum.
Yeah. If you go back to the Friedman problem, we actually wrote that down two ways. The first way was the inconvenient way, because once you've actually reached period t, the value of this Lagrange multiplier is kind of is polluted by the amount of time that's elapsed since you took the decision. And of course, you can re-optimize every period. The reason why we do this is because effectively, every time you hit a new period t, you can re-optimize. So what's really immediately relevant, given my information in period t, is these three conditions I'm writing down. But it is a sequence, it's a plan, it's a policy. And if the environment's stationary, I won't change my plan, I'll just change my decision when I get the information. Okay, so what is the value of using the log gives me this wonderful first derivative, which is 1 over ct. All right, so that's, look, it's decreasing in ct. That's kind of what we think the marginal utility does. It's decreasing in a certain way, which may not make all of you happy, but that can be fixed. You can just choose a more complicated function than the log. And it's independent of past consumption, so it's a time separable, confirms the time separability. But the most important thing you should remember is that the lambda t has a very, very clean interpretation, which is robust in macro in these kind of problems. It's the marginal utility of a relaxation of the resource constraint in period t. But it's also the marginal utility of consumption. Because in this problem, I'm maximizing my utility using consumption today. Okay, so that's a really important first order condition. And the second first order condition involves the path of capital from t to t plus 1. It's the foregone consumption. What am I getting out of that? Well, if I gave up a unit of corn today, I would lose lambda t, but I would gain the value of its planting tomorrow in expected terms. I can't tell you what the productivity of that corn is going to be, but I know the production function, and I know how the production function is shifted by this theta, so I can pretty much go and figure that out. Okay, so again, this looks like the capital asset pricing result we had before. This is the Euler equation governing lambda. And remember, alpha is the elasticity of output with respect to the corn that's saved. Beta is the measuring the impatience or the patience of Robinson Crusoe, and the expectations operator is conditioned on t information. And there's a bunch of uncertain stuff in there. Maybe some of it we can factor out, but in the end, we've got stuff that's random in there. Okay? Okay. The last first order condition is just the derivative of the Lagrange with respect to the Lagrange multiplier. So the resource constraint is binding, and it will be binding in this problem because Crusoe will always value extra consumption. Okay, so that's a clean set of answers. Make sure you understand this is worth investing some time in. Do it yourself. Okay, make sure you understand what's going on. And there's sequences. Every year, one of you kind of forgets that this is a sequence of first order conditions. It's not just 3. Okay, it's true for every t from t equals 0, bump, 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 t plus 50, etc. Even though they're plans from the perspective of t equals 0, you have to state them. Now again, in this special case, for illustration, you can actually solve this model. There are a couple of other examples when you can do this. One is linear quadratic. So I can state the whole thing in linear quadratic terms, and I can get a closed form solution. I can also, there's a case, I think Sally Martin or somebody in that generation proposed it, linear production and log consumption, log utility and depreciation. Note we have 100% depreciation in this problem, right? Everything, if Crusoe doesn't plant the corn, it's gone. He either eats it or plants it. There's no like putting it in the silo, putting it in your shoe. It doesn't work, okay? But if you have linear production, you can actually have depreciation. So it's a bit of a trick. Or you can make the depreciation equation a log linear relationship. So that's a trick that was used by Ben Assi in a paper that goes way back to the 2000 or something. Okay, so they're tricks, but these are all, ultimately we're pointing to the idea that we're going to have to eventually approximate everything. So next week, when you start with Lutz, you'll see that, you know, you'll be approximating stuff. But still, it's nice to have this problem. So what I've done here is I've substituted for lambda. I've eliminated lambda, right? That was one of the big objectives. The crutch of the Lagrange multiplier has been purged from my economic analysis. Okay, isn't that wonderful? Okay, so the marginal utility on the left-hand side of giving up 1 unit of consumption is equal to the marginal gain of doing the same thing, planting it in the ground, getting some unexpected return, and taking expectations of this, this marginal product times the unknown marginal utility of consumption in the second period. So if you remember, the expectation of a product is not equal to the product of the expectations, right? So that's why, you know, going from this step to the next requires explicitly looking at those things. But remember, in this case, we've got some special assumptions. It'll be possible to solve this thing completely, okay? And I'll show you how to do that. So, formally, multiply both sides by kt plus 1. Okay, and if you do that, you can see that and kt plus 1 is actually deterministic. It's not random. There's no rat crawling into the silo and before he plants it, eating up the corn. So there's no randomness. So if I know what I plant, I know what I can consume today, and vice versa. That's just a statement of the resource constraint. So I can actually, if I pre-multiply by kt plus 1, I can actually fold it into this expectations operator. And given the form of this production function, actually, we can actually write that as yt plus 1, regardless of what it is, even though we don't know what theta is tomorrow. Okay, so what do you see that's kind of interesting here? You see y relation to c on both sides of the equation. It looks recursive. It looks like maybe we can get something out of this. Do you see? Okay, we're not done yet, but we can rearrange it because yt plus 1 is my consumption in t plus 1 plus the capital in t plus 2. So I can insert that. So yt on the left, y divided by c on the left-hand side, and what I've done is I've divided by ct into y minus ct, and then I move the 1 to the right-hand side. And then I've got this expectation of the same thing, 1, plus the capital stock in t plus 2 in relation to ct plus 1. Because that looks like a recursive outcome, because it is a recursive outcome. Okay, so, you know, and it's kind of, it's an outgrowth of logarithmic utility and isoelastic production. It's an artifact of those assumptions. Every deviation from that will give you a non-analytic outcome. That's a pretty broad statement, okay? So if I iterate this many times, I end up getting an infinite sequence, an infinite sum of powers of alpha beta. Remember, alpha is the elasticity of what? What is alpha? It's technology, it's the elasticity of output with respect to the input. Don't have to talk about corn, but you're right. It's the corn harvest elasticity with respect to the planting, if you like, but it's just the elasticity of output with respect to the input, and there's only one input. Beta is the discount factor. So this model is ironclad, immune from the Lucas critique. I mean, we know exactly how consumption behaves relative to income as an artifact in this model of technology and preferences. And the logarithmic periodic utility function is also part of that story. I don't know if you remember this, but in the logarithmic specification, intra or intertemporal, you've done this in micro, it has very special features. It implies constant budget shares, the Cobb-Douglas utility function. It also implies that income and substitution effects cancel. So that's kind of what's going on here. Again, it's not what I'm telling you is reality, but it gives you some insight, because you're going to see that we can actually get a function. But we're still not there yet, because we have the tail wagging the dog here. We've got this tail. You keep pushing it out many, many periods. You still got it there. So how do we get rid of it? Well, we want to make sure that Crusoe is reasonable and doesn't keep on accumulating corn until, time infinity. And then he says, well, gee, kind of stupid. I should be actually eating this corn. I could eat more corn every year, every period, and be better off and not affect my my holding or maintaining the budget, the intertemporal budget constraint. I'm just kind of wasting resources, because the value of that corn at some very long horizon is positive, so I can actually just eat some of it. I can make myself happier at every point in time up until capital T. So we call that a transversality condition. It's the cake-eating condition. Remember I told you about it before? It's the corn-eating or the yogurt slurping condition. Yes?
Is that comparable to the non-Ponzi condition?
Sorry?
Is it somehow comparable to a non-Ponzi condition?
No, because Crusoe's not borrowing here. He's saving. Okay?
It's like the opposite, like non-Ponzi.
It's kind of the opposite, yeah.
Reality is like what
Yeah, if Crusoe were dealing with a bank, it would be kind of it'd be like forcing Crusoe to eventually have a positive present value or non-negative present value of the budget constraint. But there's no bank in this model. Crusoe's banking with himself, basically. He can't borrow corn from anybody. But it's a good question. Keep those distinct. Those are distinct ideas, right? So if I apply that, and this is just one. Remember, there are many different, there's a whole bunch of transversality conditions I could think of. All they have to do is make sure that this last term disappears. Okay, so I can make Crusoe much more impatient or less impatient. I can just apply that condition. I just want to make that thing go away. And then what's left is this intervening infinite sum of a constant, right? Again, that's the whole, the weird thing about this setup is that it gives us this fantastic outcome. Okay, so if you just apply that and then solve this problem, you end up getting a constant share of income is consumed every period. And the share is 1 minus the elasticity of output in the production function times Crusoe's patience, Crusoe's discount factor. That thing is always going to be between 0 and 1. It's not a constant, because every period I get shocked. So if I have a great harvest, I'm going to eat more. If I have a bad harvest, I'm going to eat less. But that consumption function is very, very mechanical, right? It's a little bit like Milton Friedman's, because it doesn't have a constant in it. So it's always going to be a fraction of your permanent income, because permanent income is kind of proxied by YT in this crazy sense, because YT, even though the shock is white noise, if you have a good shock, you feel richer, you want to consume more, but you also want to invest more. So those two motives cancel out. That's the nature of the log isoelastic production function assumptions. Okay, so you were saying, why the hell is he talking about this? Well, it's kind of a nice example that will inspire you to think of deviations from this, because there are many different deviations we can imagine. But again, this is a cool result because it's closed form. I can simulate it. I can look at it. Obviously, it's going to have very special predictions for consumption and income, right? Volatility of the logarithm of both sides of this equation will be equal, but you still have consumption smoothing. People are still only consuming a fraction of their income. They're not behaving irrationally, they're behaving hyper-rationally. Okay, so KT plus 1 is a multiple. So the investment function is also a fraction of income. You have something like you could call that but it's not an accelerator, right? Because you can't store the capital. You can only just plant it. But it's still a pretty powerful result. It's atypical, okay? And again, I mention this again and again. In general, for functions you'll use in the rest of your life, you'll have to do some manipulation of the first order conditions, because the first order conditions are the key, summarizing how the model behaves in response to shocks and dynamically, and you'll have to log linearize those first order conditions. But we didn't have to do that because it's kind of already log linear. I mean, it's already kind of made for us. Okay? Now we can use the state space to look at this. So now I'm going to try to pull in all the stuff we've done throughout the last 7 weeks. We want that form. That's the magic form, the AOC form. And let's take logs. So if you take logs of this, it is linear. So it is a log. It is an exact characterization of the model's dynamics. Is a log linear. Everything else you'll be doing will be approximating, and this will you should never rely on Dynar to do this. You should do it yourself, just to make sure you got it right. So log of consumption on the left-hand side. On the right-hand side, I've got a constant and the log of the capital stock, which is deterministic today. It's known today. And this shock that appears, okay? The capital stock has the following equation of motion. If I substitute for yt, and again, this is the value of the isoelastic power function for the utility, for the production function, because you can take logs of that and it has an exact form in the product of a constant times the logarithm of the argument. Right? So this is, again, just really nice outcome. But note, now I've got kt plus 1 in terms of kt and theta t in the logarithms. I'm going to have to figure out how to get ct in the same form, because we want the state space to look like that. Remember, t plus 1. So we have to write down the state vector, xt plus 1. And this is state space in the Lundquist-Sargent sense, so it's going to include some control variables and some true state variables that Crusoe cannot change at period t. Now, we assume that the log of theta is white noise, so that means really a good harvest today has no predictive value of harvest tomorrow, productivity tomorrow, so that's it. And the expected value of the, the model is cooked in the sense that we get the log of the expected value. The expected value of theta is equal to 1. And the equation for consumption fixes the log in the stable subspace, because the consumption rule says that I'm going to consume as a linear function of other state variables. What are those state variables today? Remember, we showed that CT is a fraction of YT. So what are the state variables for, if you take the log of log of YT, what are the relevant state variables? We want to eliminate YT, I'm trying to tell you. So theta t and KT, right? The log of K to the alpha, or theta times K to the alpha is equal to the log of theta plus alpha times the log of K. And remember, K is given today. I can't change K, and I've got this shock. So that's my consumption function in this particular setup. So one plausible representation of this model in its optimal behavior outcome is selecting xt, or xt plus 1, to have 4 elements. You could leave yt in there, but it would be a trivial linear function of the other stuff, so let's just eliminate it. Again, there's no unique representation. If you want to track If you want to track YT, you can track it either in the state space or you can track it in the observer equation. Because this is a log linear model, so everything's going to be linear. Okay, so let's go through those pieces and see how they look. Okay, so lnk is is simple because kt plus 1 is a deterministic function of what I saved in CT. Okay, and that's just going to be the ln of yt minus CT. And since my consumption is a linear function of yt, what's left over is a linear function of yt. So the ln of alpha beta times yt is equal to the ln, the natural log of ab, plus a constant times ln of kt, plus ln of the random shock. Okay, that's an easy one. So we're trying to get the rows of the matrix, just like we did throughout the course and all those problems, right? Now CT looks a little bit more complicated, but we want to get CT plus 1, so we have to lead it. And then we substitute the capital, which is deterministic. And then we take the logs, and we get the following. Okay, so we'll get a linear combination of CT, that's what I did last period, a constant, and the log of the capital stock in the last period, a log of the shock in the last period, and a log of the shock in the current period. Okay? So these two last ones are easy, right? Because you're just carrying it forward. So here's a suggested representation of the system. Okay, so ln kt plus 1, you can trace it through. ln of theta t plus 1, that's just the stochastic process that Crusoe is facing. It's white noise. So it's easy. And then we've got tracking the one, and then we've got this other stuff. The one is important for the level of consumption and for the level of capital stock, but it's not important for anything else. And then the last equation, of course, is the consumption rule. Yeah.
I have a question on the white noise process. So are we assuming that, because we assume zero mean, right? But do we also assume that it has a variance of 1, or what's the assumption there? Because there's no...
We've cooked it to make variance 1.
Okay, because there's no signal present.
That's a good point. So in the completely general case, you'd want to scale up the shock. I've assumed it's got variance 1, just to make it easy. But if you want, you could put a theta in there, and then it would change you could actually move theta around. Theta. You could move sigma around, so you could scale it up by some standard deviation term, right?
Because then if we have a 1 there, because it's the log of theta, wouldn't that mean that the variance should be 0?
No. It's going to have positive variance, but we're scaling it to be 1. So let's just assume for the matter of today that we're scaling it to equal 1. But no, I think this is okay. Okay, so we can look at the eigenvalues of this problem. We need to have basically we have a constant, so we know that one eigenvalue of this dynamic system, this AO matrix, has to be 1, and we know that the other one can either be on the unit circle or outside the unit circle. And in this case, will be 2 unit eigenvalues. Okay, one corresponds to this mean of the system, and then the other corresponds to the unstable consumption, because consumption cannot take any value. This model will not be stable if Crusoe consumes the wrong fraction of output. Okay, it'll either his consumption will go to 0, or it'll explode, or he'll end up saving a lot of core, and he won't be doing the optimal policy. He won't be obeying the first order conditions. So we're basically making CT lie in the subspace formed by the other elements of xt. And we already said that CT is kind of a jumping variable. It's not bound by the capital stock. Technically, it's not bound by previous decisions made in this problem. Okay, so you can write it like this. You can generalize this. You can generalize this to have a non-white noise process, and then you have to have an expanded system of ZT, and possibly you have to worry about solving for these, which you can do using the method of undetermined coefficients. But that's more complicated than you need to know. Okay, so that's enough of that. Super simple problem, super simple solution, lots of caveats, but you can use the same problem to demonstrate the usefulness of the value function approach. Okay, so this is again taking the special Brock-Merman example and writing it like this. This is also, I think, in the textbook. Okay, so remember, k in period 0 is a state variable. So if you drop all the subscripts and just talk about period k, capital stock in period 0 is k, and the capital stock in period 1 as being k prime, then we have the potential for a recursive problem. So that if you define V as being the maximized value of expected utility in period 0, and then the expected value of expected maximized utility in period 1 is equal to V of k prime theta prime. Theta prime is the unknown value of theta in the next period, which kind of makes Crusoe wealthy or poor in the second period. Okay? Everybody get that? This is what we did last time, the time before. So this is the collapsing of the problem into two periods. Note that Crusoe's choosing C, but he can't choose C in an unconstrained fashion. He has to obey his resource constraint, or it's not a budget because it's not a market, but it's his resource restriction that governs his behavior. Okay, so that's it. I mean, theta is the current value of the shock, which is observable. Theta prime is not observable. And the EC just means conditional on the information available to Crusoe in the current period. That's C stands for current. Okay, not anything else. It's just because in the book they don't distinguish. People may get confused. What's the conditioning set? It's two periods: first period, second period. What do you have available in the first period? So see how beautiful that is? Look how simple it is. It's much simpler, but you don't know what V is. And I'm asserting that it exists, it's unique, it's differentiable. Okay? Turns out that it is, but that's a very special case. So again, this is not a highly generalizable case, but it's nice because it'll give you very similar answers as before. We could also take normally you can use Lagrange multipliers even in a two-period case. It seems like trying to open a peanut with a sledgehammer. If you have two periods, just take the budget constraint and just substitute it into the original problem, and you have an unconstrained problem. Right? See what I did? I just plugged it in. And if you're wondering where this space comes from, it's a typo that I made. I just didn't feel like retyping the. It's what we call a patch. It's a little square of white space that covers up my typo. Okay. So the maximization is now not over C, but it's over K prime. So I'm literally choosing my planting, and the residual I'm eating, and I'm getting utility from it. And I've got the advantage of knowing that my planting gives me utility tomorrow, even though I don't know what theta will be tomorrow. I know that it's going to obey the rules of theta today. And I can treat it as such. So again, under the assumption that V can be differentiated, that it's a continuous function, then I can use all the results of last week and the week before. Okay? There's only one first order condition. So not even a sequence, it's just one. So that's what people like about the value function approach. Literally, marginal utility today is equal to the marginal utility I get from deferring that consumption to tomorrow in expected utility terms, conditional on this value function, and V sub k is the derivative of the value function, partial derivative with respect to k, evaluated at k prime, my choice, and theta prime, the unknown realization of the stochastic process. You can also do this with respect to C. You don't have to use the k prime. I think it's kind of nice to do that because you get a really nice intuition, because what it tells you is that you can influence the value of the rest of your life by affecting the state variable that you inherit in that second period. So you're kind of turning a dial that affects your own given conditions that you will have to optimize over or take as given when you optimize over consumption in the next period. So you get this really beautiful first order condition. Any questions about that? Pretty straightforward. Now, I slipped into this condition before, which is a condition on the behavior of the derivative of this value function over time, and it's called the Benveniste-Schenkman equation, which is nothing but like an envelope theorem for the value function. It just says that if I'm doing the right thing now and I'm doing the right thing tomorrow, then changing the state variable, any state variable, will have a predictable path which depends on my discount rate, right? But it's again, it's linking something that's known for sure with something that I don't know in the future. So it's an expected value result. There were two questions, yeah?
On the slide before you changed it with respect to K prime.
Yeah.
Now the first order condition is with respect to C. Can you again explain why you changed back to C?
No, I didn't change back, I just substituted, right? Because
I know, but in the first order condition now it's with respect to C and not to K prime. I was just a bit confused why we did this step, this last step on that slide, and not just took the value function at the beginning of that slide.
why I didn't,
Because it's just one over C in the first order condition. And why is this middle term step?
well, we have to impose the constraint. So you cannot optimize without any constraint. That's just not right. You have to, Crusoe has to know that if he eats more today, he has less planting tomorrow. So it's just taking cognizance of that. You can do it other ways. Like I said, you could try the Lagrange approach with one Lagrange multiplier, but you're going to substitute it out anyway because you're going to be at the constraint. So you're going to substitute. You'll get the same result. This is like if you did it the other way, if you made it with respect to C, then you'd have to put C here implicitly by plugging in this expression. You're going to get the same outcome. But as I said, it makes sense for me to actually see the effect on tomorrow's true state variable you have through your control variable today. And you can think of K prime as also being a control variable, but in the future, right? So for a lot of people, this is it's kind of a stylistic problem, but you get the same answer. Okay, anybody else? Okay, so this Benveniste-Schenkman equation can be thought of as a way of teasing out the Euler equation that we would have in the other approach. It's the path of marginal utility over time. Okay, because if you look at the first equation, what does the first equation tell you? What is the English statement, the verbal statement that characterizes the first order condition? This should just roll off your tongue immediately. Remember Marshall said you have to be able to write the math down, but if you can't explain it in words, you tear it up and throw it away. So, what's the left-hand side? Jill? The marginal utility of consumption today. And what is the right-hand side?
Discounted expected utility tomorrow.
Of what?
Consumption.
Of resources, of stuff. But stuff is stuff. You can eat the stuff or you can plant the stuff, so it's the same. Okay, so you could call that wealth, marginal utility of wealth, or marginal utility of capital. Since we've written K in there, it's going to be the marginal utility of capital tomorrow. Okay, so that's the way of thinking about this. So, but what is this then? What is this thing? This has to also be the marginal utility of capital today. And that has to be the marginal utility of consumption today. So these two are equal to each other. We're eliminating this value function. That's the objective for me right now, is to get rid of, just like we got rid of lambda before, is to get rid of this helping hand, this value function. Okay? Yes, you look skeptical.
Yeah, I think I misunderstand the question, it's maybe not the best one. But so you say that the right-hand side is also marginal utility of wealth, because I would have thought of it as like an infinite value, because we have the value function there.
Well, maybe it is.
Yes.
Maybe it is. It's the value of having this extra bit of corn forever,
Yeah.
right? Because you've literally already optimized it, and that's the recursive nature of the problem. So, I mean, the point I'm trying to make is that thing, this object appears here with primes on it. It's the same function. It's just got different arguments. Okay? So again, this Benveniste-Schenkman is kind of like guiding the valuation of resources as you move through time. It's a little bit like the Euler equation in the Lagrange approach. So we have two equations that can be leaded by one term. So if you lead them by one term, just put an extra prime for the next period from the perspective of tomorrow. And you can basically, by substitution, understand that tomorrow's marginal utility of resources is going to be a function of resources tomorrow, and in period 1, as opposed to period 0, you actually have this information. You know what theta prime will be, so you can take expectations of that. It appears in the first order condition, and you can substitute it. So regardless of what it is, we can substitute it in, and we have eliminated the first derivative of the value function. Again, this is a special property of this particular problem. It is an Euler equation. It's an Euler equation for the marginal utility of consumption going through time. Isn't that amazing? I mean, I think it's pretty cool, actually. Now, if you grant me the ability to do that, I can do exactly what I did before. We can expand the numerator in brackets. We can do the same step we did with respect to the Lagrange approach, and we can write this thing as an infinite sequence. And if this is a policy rule, then it's a stable policy rule, then we can actually write consumption as a constant fraction of current income. Again, it has to be a time invariant rule. We could also use guess and verify. So this is what they do in the book. The method of undetermined coefficients. It's also a popular way of solving log linear models in general. If we think the value function has the form, if we kind of got the message from somewhere that this is the value function, it takes this form, then we can use that in the two-period problem and solve for the undetermined coefficients. The undetermined coefficients are A, B, and C. the value function, whatever it is, we propose that it's a function of the logarithm of these two elements of the state vector. If you solve the previous two problems, you know that's true because you can just plug it in and see, but we'll do this way. The first order condition looks like this. So you see that A disappears because it's a constant, and there's no role for C. Okay, so you just have to solve. You just have to solve for K prime, which is what you were controlling as a function of K, which you're observing, your current value of K, and you've got this undetermined coefficient. So if you plug it back into the Bellman equation and match terms 1 to 1, on the left-hand side, we've got A plus B times ln of K plus C times ln of theta. On the right-hand side, we have this stuff. We just have to gather terms and match the coefficients. So what do you get for B? You get alpha divided by 1 minus alpha beta. And if you plug that in, you can see that the capital stock is indeed tomorrow a linear function of a power of K alpha. This is just Y. That's just the consumption rule, the savings rule that we had in the other two previous problems. Okay, so these are just trying to knock the nail on the head with different types of hammers. You end up getting the same answer. You can also solve for A, but that's just the level. It's not very interesting to us, but you could solve for it if you wanted. And you can solve for C as well. Okay, so we've learned these three ways to go after dynamic macro problems. The complexity should be obvious to you. These are just illustrative methods. If you look in the book, they even use the Howard algorithm to solve for the policy function in this problem. Okay, I find that kind of resembles what I did for my dissertation, which was extremely painful. I mean, you iterate. Sometimes you don't have to iterate very often. Remember the Howard algorithm? What was the Howard approach? You solve for the policy. You propose that the policy has a particular form, a function of the states, and then you plug it into the value function and get the implied value, and then do the value function approach to solve for the policy function and see if the policy function is converging to something. Howard. Okay? That's in the book, but I'm not going to do that here. So, in our life as researchers, we have to confront the reality that most problems don't look like this. So we have to move away from the lamppost. We move to another brighter area under a different lamppost, which says that we take systems or models that have forms that, if you take the first order conditions, you can log linearize them. And when you log linearize them, there's a set of linear equations in true states and other variables, co-state variables, and then you can use the Lundquist-Sargent machine to solve them. Okay, or you can fold it into an equation of motion of the system in terms of the state variables. That's the way Dynar does it, basically. Okay, so this is the quote from the book that I like a lot. This is the third edition. It's probably still in there. The computational methods become very important. So this is something if you want to do this, you have to get familiar with. There are many programs that have been written now that use different tacks on the same problem. Dynar is just one example. So some of the interesting details you might want to think about is how do you, if you think there's a value function out there, it's unique, then you can try to get really close to it as an approximation of linear combinations of different functions. Sort of reduce the basis of functions to explain this. So one would be take would be to take polynomials. So instead of linear quadratic, take nth order polynomials in the state variables, and then store these polynomials, and then just keep iterating on these coefficients implied by the policy rule and the value function that's implied. So that's kind of this is an older method, as you can see, but it works. And it works for the approximation, to the extent the approximation is a good one. Sometimes these functions may have sharp turns, and that may lead to issues with the adequacy of the approximation. Yeah, so that's one way, and then there's more complicated ways which are referred to in the book. I felt it might be worth mentioning. So instead of using polynomials in the state space variables, you could use more complicated variables to approximate these functions, which have nothing to do with the state itself. Just like taking a very low dimensional space and trying to span this value function, then try to fit the value function, or try to characterize it. Okay, but there are issues with that, and there are other things you can do. So I'm going to leave that to your own interest. That's certainly not material for this part of the course, but it's just a reference that you might want to think about that. So let's do quickly the grown-up version. So this is the final model I'll show you. This is the grown-up version of the baby thing I showed you before. So the baby thing was Crusoe didn't have a labor supply decision because otherwise he wouldn't survive. So he had to work every day from sunup to sundown, planting those coconuts, planting the corn, whatever he was doing. And now we're going to let Crusoe take it easy if he wants, or maybe work hard if he wants. So let L be the fraction of time that Crusoe spends in the fields planting the corn. And this labor is unpleasant. So we need a utility function that incorporates both the gains from eating and the disutility of working. And we're going to have to characterize the shape of this u function by making some statements about the first derivative of each. So more consumption is always valuable, but it's valuable at a decreasing rate. The same is true for leisure. So 1 minus L is leisure in this setup. You can also make it directly a function of labor, negative, with a negative utility and a increasing disutility of labor. So just flip the signs appropriately. But then you have to worry about the cross derivative. So the cross derivative is kind of interesting. What does that mean? Kind of didn't make the end of the slide here, but the cross derivative, actually I don't even have it. I put this restriction on it. So I want Crusoe to have reasonable tastes in the sense that we want to allow him to have positive effects on marginal utility of having more leisure, or even negative, slightly negative. Okay, but it's most models will look at actually set this cross derivative term equal to 0. They just put them in separably, time separably. So you have a disutility of labor that's independent of your consumption level. Okay, so that's what I just said here. Okay, so that's the common way of doing it, and also in modern new Keynesian macro models. Okay, so technology is more fancy. So we've got capital. So if he plants corn, usually it's gone. Next year you have to replant. Well, now we're going to have coconuts. So you have a coconut tree, and you have a plantation of trees. That's your capital stock, and you can defer consumption of coconuts by planting these coconuts, and with some rate of success, you'll get something out of it. And this is a Herod-neutral form of technical progress. Remember, in economics, master's students know this already, three ways of modifying productive, exogenous productive change. One is this one, which has very nice features, Herod-neutral technical progress. It can be growing. We can have solo-neutral technical progress, which is probably unreasonable as a long-run phenomenon, but it could shift the productivity of capital. So put Z on K instead of on L, and that would be solo-neutral technical change. And if you put it outside the production function, that would be Hicks-neutral technical change. So you do that, you've kind of spanned the space of technical change that we play with in macro. Capital depreciates now, so it's around and it disappears at some rate delta, and you know that, and you can take advantage of that. So your consumption set is literally, you can take the entire capital stock into the next period except for delta, and you can save. If you don't save, you can consume. And we're going to assume that agents have the wide range of possibilities, including eating the capital stock if need be. So a lot of people get excited about this. We still do. We don't know what ZT is doing. We have to make some assumptions on it. We can have deterministic growth because this is the only reason the economy gets bigger. Well, the reason the economies get bigger is because they get more people holding capital stock per capita constant, or we need more capital. And the third possibility is that given labor and capital, we can actually get more output. Okay, and if you take that view, then you have to make some assumptions about how Z is growing over time, whether it's stochastic or whether it's deterministic. The deterministic is kind of easy. If you look at that, if you take logs of that, we'll get very close to what we had before. You have a deterministic part of Z that's growing at a growth rate G, and then it's getting shocked occasionally. Actually, not just occasionally. Every period is getting shocked by epsilon. Okay, so take logs. That's kind of a standard set of assumptions: deterministic growth, an initial condition, and some randomness. And epsilon could be a stationary stochastic process with mean zero. Okay, it could actually have moving average parts and autoregressive parts. And we tend to cheat because you'll see in this model we can't get really good business cycles. That was the critique, the spectral analysis critique of Cogley and Nelson and some other people, saying that only if you make this thing have a certain behavior can you really get a business cycle that looks like a business cycle. So that's why the real business cycle agenda kind of failed. It really didn't do a good job of getting the right kind of persistence in the business cycles. Now the alternative is to have stochastic growth. So that would be basically like a random walk in the logarithms. This thing is just kind of wandering. You can even put a drift in there if you want. But we're going to go for the easiest, just to get the point across. Everything else you can do afterwards. But once you get the data and you try to calibrate a model, you'll have to worry about this. You'll have to worry about taking the trend out, to use the Hodrick-Prescott detrending method, or to use something else. These are all like interesting issues. So I'm going to use this function, logarithmic utility over consumption, and I'm going to use a sort of a Hara type of function or isoelastic function of leisure. Now, why would I want to do that? Why would I want to do that? Well, I want to give this agent some taste over leisure that's a bit flexible to make this agent want to work possibly more or less in response to economic incentives. So back in the day, Killen and Prescott were thinking, maybe in good times agents work hard when the wages are kind of high, and maybe I haven't been working for a while. Maybe I'm eager to work, or maybe I don't respond at all to. Maybe I just want to work my 8 hours a day, and wages don't matter to me at all. Incentives don't matter. Okay. Maybe even they matter in the wrong way. So if I get a good technology shock that's really durable, I'll feel so rich that I'll actually stop working. I'll hold back my labor because the income effect or the wealth effect is stronger. So think of this eta is related to the Frisch elasticity of labor supply, how I respond to changes in the incentive to work. And then if you have technology, we'll use the Cobb-Douglas production function. This is very common, okay? Because in a market economy, the long run of this economy in the market economy would be characterized by constant labor share and constant capital share along a growth path. And that's why Harrod-neutral technical progress is important. In the Cobb-Douglas case, it's isomorphic to a model with Hicks neutral technical progress. But if you generalize from the Cobb-Douglas, the only way you can get capital factor shares to be constant over the long run is to have Harrod-neutral technical progress. But technically, those are the elasticities of output with respect to capital input and labor input. So think of this as the raw labor, and this is the accumulated wisdom of the laborers. Think of ZT as the effectiveness. So often ZT is called effective labor, right? And along a growth path, the marginal product of labor is dependent on Z. So as we have technical progress, workers get more wages. That's the great characteristic of Harrod-neutral technical progress, right? Labor reaps the benefit of technical progress directly through its marginal product at the exclusion of capital. Okay, so now Robinson Crusoe is kind of a high-tech guy now. He's solving a hard problem. He's choosing sequences of consumption. And I apologize for the typo. I think I've got a small c and a large c, but just I'll fix that. So the same kind of present discounted value of utility using beta as the discount factor, which is deterministic. But now Crusoe gets this disutility from work and utility from consumption, has a given capital stock and a given value of technology today, and we have this describe ZT as we want, some sort of stationary stochastic process in the logs. And every period, Crusoe has to obey this. Crusoe cannot consume goods that violate, in a way that violates this constraint, given the planting that Crusoe wants to have in T+1, or the capital stock in T+1, Crusoe cannot consume more than the available output today and the available capital hasn't depreciated yet, subtracting that planned capital stock in the future. Okay, so it's a governing his resources. So this is what we call a regular economy. It's idealized. Everything's, you got constant returns to scale. Crusoe's a smart person, understands the information, the relevance of information available in time t, understands his production function, understands his own preferences, and you can actually claim this is this optimum that Crusoe, as a central planner, enacts would be replicated by a market solution. Okay, so we can use either one, right? So why don't we just use the Bellman approach just for fun? The Bellman equation, if it exists, has to satisfy that condition. So again, it's just a two-period problem. The value today of my maximized expected utility is equal to the maximization that I would take over CT, given that I understand the effect of CT on tomorrow's resources, and the additional control I have, which is LT, given that I know that my LT will affect my resources today and my resources tomorrow through the stated transition equation for capital. Okay, everybody? It's a very clear extension of what we just did. And now I've put in this very cute little assumption on, which is what Kidlin and Prescott did, and people have done. Even in new Keynesian macro models, we assume a TFP process, or here a Hicks, a Harrod neutral technical progress process that is AR1. So rho has to be less than 1 in absolute value to get stationarity. Okay, again, 2 first-order conditions, not 2 sequences. If you did with the Lagrange approach, you'd have sequences, you'd have to track the lambda, and eventually you would eliminate it. But this makes it really clear that this can be useful. So if you have a problem, you want to do it this way, do it the other way, and compare your outcomes. So the first-order condition is very, very similar to what we had before with the Brock-Meerman problem. Marginal utility of consumption on the left-hand side, marginal utility of resources today on the right-hand side, valued today, expected tomorrow. So it's the marginal utility of consumption today is equal to the expected utility tomorrow that I get from this deferred consumption, discounted back using beta. Second one is different. Second is new. It says the marginal utility of not working today, marginal utility of leisure today, is going to be equal to the cost of that, which is if I don't work today, there'll be less stuff tomorrow in the form of resources because I will not have worked, and the resources tomorrow will not be there. To what extent will they not be there? They will be not there because I didn't work today. That's the marginal product of my labor today times the resources, and this is deterministic, times the value of resources tomorrow that I could have had I worked more today. That's the second first-order condition. Now you can see that we can combine these two because they're all kind of guided by this marginal value of the marginal utility, expected utility of resources today, valued today, accruing tomorrow. This term appears in both first-order conditions, so we can eliminate it. And what's left is an intratemporal optimality condition. Okay, this is like Crusoe today, sort of weighing 2 different possibilities. One is I work harder today, and the other is I consume today. And the relationship between the two is actually the marginal productivity of Crusoe's labor today. So you can think of this as stating that the marginal utility of labor on the left-hand side is kind of the marginal utility of leisure on the right-hand side. Because if you work more today, you get something. You can either put it into the mill tomorrow and have capital tomorrow, or you can eat it today, and that would be the left-hand side. Okay, so this doesn't have any V anymore. V no longer appears. And in a decentralized market economy, what do we know about the marginal utility of what do we know about the marginal product of labor? So we've just introduced, Crusoe couldn't change labor, couldn't vary labor in his life, but here he can. This is the marginal utility, this is the marginal product of labor. So what would that be in a decentralized economy? It would be like the wage, right? It'd be the real wage. So if you want to decentralize this economy, this term would correspond to, say, W over P. P is the price of goods in terms of money. We don't have any money in this economy, so it's just going to be the real wage. Right? So this is the real wage, and you can think of this real wage as being valued at the marginal utility of consumption today, because the real wage is paid in consumption goods, and that should compensate you for not working at the margin on the right-hand side. Okay, so you can also do the Benavista-Schenkman trick, and you get the same type of expression involving successive derivatives of the value function with respect to the capital argument in in successive periods linked by beta. And then if you lead the first order condition for consumption and substitute it back, you can eliminate the value function completely from this, and end up getting the marginal utility of consumption today is equal to the expected marginal utility of consumption at the optimum discounted back using beta. This is the Euler equation. Should look familiar to you because we've done it a jillion times. Okay, so we have the Euler equation, right? If you like to do the lambda trick, just substitute lambda t for 1 over c t, and that's the generalized form of this problem you'd get in general problems. So even if you didn't have logarithmic utility, you'd put a lambda t plus 1 and a lambda t here, and you'd get an Euler equation for lambda, the marginal utility of resources or of income in a market setting in the problem when you're at the optimum. Okay, so that's a sequence. As you can see, it's true for t, it's t plus 1. You can actually string it out. And there's the interpretation. So we got rid of the value function. This is not a closed form, obviously, right? We know that if we put in the marginal product of capital using the Cobb-Douglas assumption, we can make it look a bit more familiar, but it's still not solvable because there's no closed form. That's why we did the Robinson Crusoe with the very simple world where you work 1 unit of time and you get the corn and you plant it. Okay, so in more complicated situations, we'll have to take that first order condition, take the logarithms of it, and then linearize what's inside the expectations operator, take the expectation of a linear thing, which will be linear in the expectations, and then we can write that in the state space form if we want. Okay, so what does this do for us? Well, there's my famous colleague, Harold Uhlig, who was my colleague 15 years ago, very cherished colleague, somewhat tough on graduate students, much tougher than we are in the Schumpeter seminar. He and I started the Schumpeter seminar. So this is a great paper. I don't think he ever published this paper, but Harold is a big fan of the real business cycle. So, because he thinks it does embody the Lucas, it respects the Lucas critique in ways that many others don't, and it has some interesting aspects. So this is an impulse response to a one-period shock in technology. Just watching how it just runs out through time. It's the model I just showed you, but it's log linearized. So we can look at local behavior of this thing after one shock, or I can simulate it with a shock every period following some stochastic process. You can do all sorts of crazy stuff with it. But just look at this as a qualitative summary of what happens. Output moves the most. Labor moves a lot. That's already kind of similar to what we have in the data. Labor moves a lot. And if you're in the Robinson Crusoe world I showed you before, labor is constant. And if you have logarithmic utility of leisure, labor will be constant. So that's kind of a weakness. That's why we have to have this Frisch elasticity. So in this planned economy, the social planned economy or the decentralizable economy, a technology shock raises productivity of labor. Workers work harder, and they do so because it's worth it, because for a brief period of time they're getting paid more, they're more productive, but that productivity dies out. Okay? So the representative agent knows that, works very hard in response to this technology shock, and he also uses the opportunity to build up the capital stock because goods are cheap in terms of labor. So he goes for it, he builds up a capital stock, produces more, and is able to elevate consumption for some time above the original steady state value. So you have a jump effect, just like we have in the Hall-Friedman problem, because the agent knows now that there's an opportunity, and the agent will take advantage of the opportunity for some period. So the agent enjoys higher utility, which is smoothed over the extent. Of course, the agent's working harder. It's kind of a disadvantage. the agent runs up the capital stock, builds up the capital stock, so the agent can take advantage of this more productive environment, because carrying the capital stock into the future means that I can produce more, and that's why the agent feels richer from the get-go, and still smooths capital with respect to investment and output. So that's kind of matching a lot of the important aspects of the model. So that's kind of why people were attracted to this model. And you still have puzzles. Even if you put money and frictions, like you will in the weeks to come, there are puzzles that still exist. We need investment, and we need technological total factor productivity. We need labor, all move in the same direction. Investment moves a lot more than consumption in the real world. New Keynesian models have difficulties accommodating some of these facts. Sometimes people don't want to talk about them, but it's still a problem. Okay? But of course, there are problems for the RBC model that I already talked about. So, you can think of the world as being divided. I tend to think of the world as being united. I think we learn from our respective difficulties and mistakes. The biggest problem with the RBC model is the assumption of the behavior of productivity. The underlying shock has to have some persistence, otherwise the agent doesn't have an incentive to work harder, invest, and do the rest, because the agent has to expect over some period of time there will be a continued high level of productivity. The production function is at a higher level for some period, okay? That's kind of considered a weakness, because you don't want to assume the answer. You want the model to generate what's called endogenous or internal propagation. You want the model to be able to generate the spectrum that we talked about. And this model is not very good at that. So the big critique of this, looking at the frequency domain, is that, sorry, this is not what the business cycle looks like. The business cycle doesn't have this spectral peak at around, say, frequencies corresponding to a period of 20 to 28 or 32 quarters. It doesn't look like that at all. Okay, this model generates a spectrum that looks like the spectrum of AR1 interacting with capital. So it has very, very low frequency, and you can tweak the values of this model and you don't get very close. So that's a kind of a standard critique of this model. You can do all sorts of other things. Okay, so you can add money, credit, and banking. You can add money. That's the most important thing. So you think of money as being relevant only if prices in terms of money and of goods in terms of money don't react instantly. So you have to have some reason for non-neutrality of money. Maybe because they're price setters. Maybe they have market power. They set prices of goods in terms of the monetary unit. Therefore, if the central bank lowers interest rates, this will have real effects. People can't anticipate that inflation will match, or price level will match these changes one-to-one. So all these things will be subject of the following lecture. But we can add lots of bells and whistles. So we can add ways to get more endogenous propagation. So habit formation. So instead of utility over consumption, you might assume that you get utility over consumption relative to some baseline, or relative to what other people are doing, or relative to what you did yourself in the past. So these are all very clever ways to get more persistence. You can add cost of adjusting the capital stock. Okay, so that's something that's been very popular, but also criticized. You can add just a fact that it takes a certain number of periods to build the capital stock. So if you want to build a factory, it's going to take you 4 periods. It's going to take you 4 quarters, or it's going to take 8 quarters to build the Tesla factory. It will be done. And back in the day when Kidlin and Prescott introduced that, it was very difficult to solve these models. Now it's very easy. Okay, so that's something you could do. Or you can add multiple types of capital. One of my favorites, I've done some work on this, is adding labor market frictions. So you make it difficult for unemployment to evolve very quickly. It's not just the complement of labor supply. because maybe people want to have a job and can't find one, and it requires some time. So you can add dynamics in that way, and you can add a financial system. The last 10 years have been very productive since the financial crisis, adding banks, intermediaries. But then, so how are you going to do that? What do banks do? Banks are intermediating. How can you intermediate if you have a representative agent? It's kind of ridiculous, right? So you have to automatically start thinking about a banking community, or maybe some people have thought of really ingenious ways of still having a representative family with bankers in the family. They go off and do their thing, bring the money back. Because in the end, you have to, anytime you add a second type of agent, you have to track that agent's wealth. You have to track that agent's decision. It gets really nasty. And they're trading with each other, right? They're also dealing with each other. But then you can address issues like inequality. You can address long-term, you can even address long-term inequality. So, this is the future of macro. So my last comments, we've really pushed the limit in terms of the real business cycle. You will add money to your purview, and you'll learn all sorts of neat things. And there's these two papers. If you're interested right now to see what you're going to see in the next few weeks, I predict that what you learn will be very correlated with these two papers. So they're just surveys. One is a European perspective, the other is an American perspective, U.S. American perspective. And they include a lot of the bells and whistles that people throw into these models. But now we're moving into a new age where more popular approaches are based on these older papers that just have different classes of agents that have different problems. And sometimes they can't borrow. So one of the most productive ways is to let you behave like Robinson Crusoe, and then the other family has to basically can't go to the bank. There's no access to credit. So those agents really have to consume their income. And that seems to be very realistic. That's something we observe. There's a huge fraction of the US population has no bank account, right? Imagine living off cash, selling your paycheck to a payday gangster, that happens. So if you have that type of heterogeneity, you're going to have some consumption responding very, very sensitively to income, and the rest will be smoothing like crazy. So that's an interesting insight. But it's possible to solve these models numerically. Okay, so I would ask you to go home and read this fantastic quote of Joseph Schumpeter, after whom our seminar is named, but he never came to Berlin. So we called this, Harald Uhlig and I named just the Schumpeter seminar as a provocation because he was from Bonn, okay? And he always wanted to come to Berlin, but never got the offer. And then eventually he went to America and did much better. So ironically, this applies to other colleagues that I've had. He basically says, all the stuff I've been talking about these past 8 weeks has been about self-reproducing environments, recursive economics. So Joseph tells us we should kind of step outside of that box. I think he kind of understood back then in the 1950s that too much attention to this type of analysis might distract us from paying some attention to history. Economic history being something that never repeats itself. So, it's a matter of opinion. I think we've repeated the financial crisis of 1929 to 1932, but we reacted differently this time. Some would say maybe it's because we learned from history. In a meta sense, we have to think about models that transcend the historical detail. But if you like that, stick with us, and if you don't like that, do economic history. But don't forget what Joseph said. Okay, so good luck with the rest of the course. You'll enjoy it. Show up here on time, and I will too, at my great displeasure. See you later.